At the end of this video, you should be able to list basic SI units and the quantities they describe, and convert measurements into scientific notation. Chapter 1, Section 2, Measurements and Experiments. Numbers as measurements. Physicists perform experiments to test hypotheses about how changing one variable in a situation affects another variable. An accurate analysis of such experiments requires numerical measurements. Numerical measurements are different than the numbers used in a mathematics class. In mathematics, a number like 7 can stand alone and be used in equations. In science, measurements are more than just a number. For example, a measurement reported as 7 leads to several questions. What physical quantity is being measured? Length, mass, time, or something else? If it is length that is being measured, what units were used for the measurement? Meters, feet, inches, miles, or light years? The description of what kind of physical quantity is represented by a certain measurement is called dimension. You are probably already familiar with the three basic dimensions: length, mass, and time. Many other measurements can be expressed in terms of these three dimensions. For example, physical quantities such as force, velocity, energy, volume, and acceleration can all be described as combinations of length, mass, and time. When we learn about heat and electricity, we will need to add two other dimensions to our list, one for temperature and one for electric current. The description of how much of a physical quantity is represented by a certain numerical measurement and by the unit with which the quantity is measured. Although each dimension is unique, a dimension can be measured using different units. For example, the dimension of time can be measured in seconds, hours, or years. SI is the standard measurement system for science. When scientists do research, they must communicate the result of their experiments with each other and agree on a system of units for their measurements. In 1960, an international committee agreed on a system of standards, such as the standard shown in Figure 2-1 on page 10 of your text or on the screen now. They also agreed on designations for the fundamental quantities needed for measurements. This system of units is called Système International des Unités. Forgive my butchering of that. SI. In SI, there are only 7 base units. Each base unit describes a single dimension, such as length, mass, or time. The base units of length, mass, and time are the meter, kilogram, and second, respectively. In most measurements, these units will be abbreviated as m, kg, and s, respectively. These units are defined by standards described in Figure 2-2 on page 11 of your text or on the screen now, and are reproduced so that every meter stick, kilogram mass, and clock in the world is calibrated to give consistent results. We will use SI units throughout this book because they are almost universally accepted in science and industry. Not every observation can be described using one of these units, but the units can be combined to form derived units. Derived units are formed by combining the 7 base units with multiplication or division. For example, speeds are typically expressed in units of meters per second, which is to say meters divided by seconds. In other cases, it may appear that a new unit that is not one of the base units is being introduced, but often these new units merely serve as shorthand ways to refer to combinations for these units. For example, forces and weights are typically measured in units of newtons, represented by a capital N. But a newton is defined as being exactly equivalent to 1 kilogram multiplied by meters per second squared. Derived units, such as newtons, will be explained throughout this book as they are introduced. SI uses prefixes to accommodate extremes. Physics is a science that describes a broad range of topics and requires a wide range of measurements, from very large to very small. For example, distance measurements can range from the distances between stars, about 100 quadrillion meters, to the distances between atoms in a solid, 0.000000001 meters. Because these numbers can be extremely difficult to read and write, they are often expressed in powers of 10, such as 1 times 10 to the 17th meters, or 1 times 10 to the negative 9th meters. Another approach commonly used in SI is to combine the units with prefixes to symbolize certain powers of 10, as is illustrated in Figure 2-3 on the screen now. The most common prefixes and their symbols are shown in Figure 2-4 on page 12 of your text or on the screen now. For example, the length of a housefly is 5 times 10 to the negative 3rd meters, which is equivalent to 5 millimeters, represented mm. And the distance of a satellite, 8.25 times 10 to the 5th meters from Earth's surface, can be expressed as 825 kilometers, represented as km. A year, which is about 3.2 times 10 to the 7th seconds, can also be expressed as 32 megaseconds, represented with a capital M lowercase s. Converting a measurement from its prefix form is easy to do. You can build conversion factors from any equivalent relationship, including those in Figure 2-4. Just put the quantity on one side of the equation in the numerator and the quantity in the other side in the denominator, as is shown on the screen for the case of this particular conversion. 1 millimeter is equal to 1 times 10 to the negative 3rd meters. Because these two quantities are equal, the equations at the top of your screen are also true. Thus, any measurement multiplied by either one of these fractions will be multiplied by 1. The number and unit will change, but the quantity described by the measurement will stay the same. To convert measurements, use the conversion factor that will cancel the units you are given to provide the units you need, as is shown in the example on the screen now. Typically, the units to which you are converting should be placed in the numerator. It is useful to cross out the units that cancel to help keep track of them. If you have arranged your terms correctly, the units you are converting from will cancel, leaving you with the unit that you want. If you use the wrong conversion, you will get units that don't cancel. Both dimension and units must agree. Measurements of physical quantities must be expressed in units that match the dimensions of that quantity. For example, measurements of length cannot be expressed in units of kilograms, because units of kilograms describe the dimension of mass. It is very important to be certain that a measurement is expressed in units that refer to the correct dimensions. One good technique for avoiding errors in physics is to check the units in an answer to be certain they are appropriate for the dimension of the physical quantity that is being sought in a problem or calculation. In addition to having the correct dimension, measurements used in calculations must also have the same units. As an example, consider Figure 2-5a, which shows two people measuring a room to determine the room's area. Suppose one person measures the length in meters, and the other person measures the width in centimeters. When the numbers are multiplied to find the area, they will give a difficult-to-interpret answer in units of centimeters times meters, as is shown in Figure 2-5b. On the other hand, if both measurements are made using the same units, the calculated area is much easier to interpret because it is expressed in units of meters squared, as is shown in Figure 2-5c. Even if the measurements were made in different units, as in the example above, one unit can be easily converted to the other because centimeters and meters are both units of length. It is also necessary to convert one unit to another when working with units from two different systems, such as meters and feet. In order to avoid confusion, it is better to make the conversion to the same units before doing anything arithmetic.
Imagine you are buying new carpet for a room. You need to tell the flooring company how much material you will need. The answer can be found by measuring the length and width of the room and then multiplying the two measurements to find the area. If the woman on the left measures her distance in centimeters and the woman on the right measures in meters, we have a problem. The units do not make sense because they do not represent the area the carpet must cover. If both women measure in meters, the answer is much more useful. Now you know how much carpet you will need.
Sample problem. A typical bacterium has a mass of about 2.0 femtograms. Express this measurement in terms of grams and kilograms. Note the given. Mass is equal to 2.0 femtograms. Note the unknowns. The mass in grams and the mass in kilograms. First, we need to build conversion factors from the relationships given in Figure 2.4, which is on page 12 of your textbook. The two possibilities are 1 times 10 to the negative 15th grams over 1 femtogram, and 1 femtogram over 1 times 10 to the negative 15th grams. Only the first one will cancel the units of femtograms to give the units of grams, as is shown on the screen now. Referring to our previous answer, we can use the same process to cancel the units of grams to give the units of kilograms, according to the process shown on the screen now. At this point, you should be able to list basic SI units and the quantities they describe, and convert measurements into scientific notation.